This is the third part in a series of videos I'm posting on how I'm going about designing and developing a 64k SRAM card for the Altair 8800 computer. I thought it would be interesting to go through the process and post the videos as I proceed so you could see how I go about doing this. Now, I should point out at this stage that this is not normally how I would develop a commercial product. Most of the products that my company develops are way too complex to put onto a breadboard, and also they tend to be RF products, which obviously don't lend themselves to this sort of development. They're normally developed entirely on the CAD system. We then have prototypes made and they're tested and any bugs or errors dealt with at that stage. But I thought it would be interesting for anyone that hasn't seen this process or is unfamiliar with developing this type of circuit to see the process in some detail, and also to see the individual circuit blocks being tested as they are produced. It gives you an insight into the thinking behind this type of process, even though it would normally be done on a CAD system. The thinking behind it is still very similar, it's just that we don't normally go through this physical implementation on breadboard at each stage. So if you saw the last video, you know that we got as far as designing the basic logic for the memory card. So this is the circuit that will enable the 8800 to be able to control the card through the various control lines that are generated on the backplane of the Altair. But if you recall, one of the requirements for this design was that we could select the different blocks within the memory card depending on how we wanted to set the card up. So in other words, the card was to emulate 1 to 4 16k cards, but in any order or any combination. And that's what this video is going to detail, is how the decoding to achieve that will be worked out. And I'll detail the design of the circuit that will enable that decoding to give us that functionality. So firstly, if we look at the original design, we see that the decoding logic was fairly complicated, and although I'm basing the card loosely on this design, the decoding circuit that I've come up with is entirely different. There are generally two ways of developing logic circuits when you have a starting point. One is an additive process where you add more logic gates and more to the design to get the extra functionality that you want. But there's also a second option which quite often works a lot better, and that's subtractive logic. And what you do there is essentially look at what you already have and see if there's a way you can reuse some of the components to build into the circuit the extra logic functions that you're looking for. That's the process I favour because it generally results in a cheaper product and a simpler product. And also, when you're looking at a board like this where the timing might be fairly critical, it's far easier then if you do need to add something for timing purposes rather than try to subsequently have to remove something. So if I look at the logic table that we're trying to achieve, one of the other design points for this board was that rather than using one 64k SRAM, I decided to use two 32k SRAMs. And if you recall from an earlier video, that was so that if the user only wanted a 32k board, they could omit the extra components and save a bit of extra money while building it. So that means that the decoding circuit has to do two things. It has to be able to decide which of the two chips to select, and then it has to decide if it needs to select any of the two banks within those chips. So effectively each chip is divided into two 16k blocks, and so the decoder circuit has to decide which of those blocks within a particular chip to select and which chip to select based on the address that's on bits 14 and 15. So it sounds quite complicated, but when you start building the circuit it works out to be relatively straightforward. So this is the circuit that I've ended up with. It looks fairly complicated, but it's relatively straightforward. It's only 3 low-cost ICs if you discount the input buffer, but we would need that either way, so it's really this part of the circuit that we are trying to make as efficient as possible. And essentially the way it works is it looks at address lines 14 and 15 and determines from those combinations which of the 2 chip select lines coming out of these 2 gates to enable, so they're active low, and then the switches and the extra gates allow us to essentially disable 16k blocks within those combinations. So I won't explain it in too much detail because it's probably fairly obvious how it works. If you do want me to go over this in more detail, then drop me a comment. Otherwise it's just really a case of the 2 halves of the circuit being the same apart from the additional inverter that we have up here that enables the 2 circuits to work as mirror images in terms of functionality. But also the 2 chip select lines coming out aren't much use to us. We could feed those directly to the memory chips, but then we'd have no way to control when the memory chips were enabled, and we don't want them to be enabled all the time, otherwise we'd end up accidentally writing data into them. So the way this works is we have the master chip select line which comes out of the logic circuit that we designed in the last video, so that's coming out at this point, which is marked as test point 2. So this line goes low whenever this particular board has been selected and we're trying to enable the RAM on the board. That line is then used to control these 2 gates in such a way that when this goes low, it's effectively enabling these 2 gates, and then depending on which of the 2 lines going into these gates is also low will determine which of the 2 outputs goes high, and they are mutually exclusive. Only one's ever going to be low at any one time. So the output will go high whenever the 2 inputs on a particular gate go low. But also we want active low lines, so we just use the second gates in this chip as inverters, and then we end up with the 2 chip select lines that we actually feed to the memory chips. So in operation what we get is this functionality where, depending on the position of the switches, we will select the particular chip, and then the particular bank within the chip is selected by having a 14 fed to the 2 chips at the same time. The 2 switches operate by effectively overriding one or other input to these gates, and that enables the particular 16k block within each chip to be either actively selected or permanently deselected when the switch is open. So for example, if both of these switches are open, this output is permanently low, and that means that this chip is effectively disabled. So the same is true with this one. It works in the same way, except that it responds to the other combination of the A14, A15 address lines, where this will then select or not select the second memory chip. So it's very straightforward. We have master select, and then there are 2 chip selects. These are gated by this signal, and then if a particular chip select line is active, that particular device is selected. So I built this circuit onto this breadboard, and I'll demonstrate the way that the circuit operates. Currently all the switches are on, so we should always select one or other of the 2 devices. If we look at the schematic, I've marked them red and blue, so the red LED is chip select 1 and the blue LED is chip select 2. The yellow wire is A14, the green wire is A15, and then the blue wire is the master chip select, which is this line. So as long as this line is high, then neither of these 2 chip select lines should ever go low. So the LEDs are on when these lines are low. So I've got this line set to high, so essentially we have both the chip selects disabled, so wherever I put the address lines, nothing happens. Both chip selects stay inactive. If I put the master chip select to low, bear in mind we have all 4 switches on, then what we end up with is, with address, this is lines 14 and 15 remember, but with address 00, then chip select 1 is on, which is what we'd expect. So if we look back at our logic table, then 00 we have chip select 1 active, and that is for block 0 to 16. If a 14 then goes high, then this should still be on, because remember we have all the switches on, so that's on. I'll put that back to 0. If a15 goes high, then it should select the first block in the second chip. So I'll move a15, and now you can see the chip select line has gone low for the second chip, and if I move a14 to 1 as well, it stays on. So you can see we have currently all the blocks selected within the decoder. If I now turn off all but the first, so now we only have the first 16k block turned on, then firstly it should be under the control of the master chip select. If I move that back to positive, then we deselect the chip, and if I move the A14, A15 jumpers to any other combination than 00, then the LED should both be off. So in that position it's off, in that position it's off, and in that position it's off. It's only active when we have 00 on the address lines going in. If I also, for example, wanted block 3 to be enabled, so that is the lower block in the second chip, then we should have the same thing here. Just chip select 1 low when the address is 00. If I move A14 to 1, then this should go out, but because we still haven't selected the upper chip, then the blue LED should stay off as well, which it does. And now if I move the A15 line to a high, then this LED will actually stay off because we also have a 1 on A14. If I now move A14 to ground, we can see that chip select for the second chip is now active, because we have a combination that is selecting the lower 16k of the second chip, and of course if the master chip select goes high, then it all goes off again. So in other words, this circuit is now doing exactly what we want as far as decoding. It's responding to the control logic, so the chips can be completely disabled until they are required, but also we're getting the proper selective combinations depending on the memory address that's fed in and the position of the bank select switches. So that's it for this video. As I said, if you want me to go over any of this in more detail, then let me know, but this part of the circuit is now done. We have all the chip select lines sorted out, we have the control lines sorted out, so the next part of the process is to start looking at the actual memory chips themselves and get those hooked up so we can start trying to write some data and recover some data from them. Okay, so that's what we'll look at in the next video.